Welcome to Big Ideas, Algebra 2 Honors. This is section 2.4, which would be modeling with quadratic functions. So modeling can mean story problems. Modeling also can mean finding the equation from the graph or finding the equation from a table of data. So we want to be able to, in this case, write the equation of a parabola given either a vertex and a point, or the x-intercepts and a point, or any 3 points on the parabola. And so each one, because we know different pieces of information, we can attack it a little bit differently so that we can do the problem in the most efficient way. So first we're going to start with writing the equation of a parabola given the vertex and 1 point. Here would be an example. If I know that the vertex of the parabola is 4, 2, and I know the point 0, 6 is on the parabola, I would want to first pick what form makes the most sense to use. And the form that would make the most sense to use is vertex form, since I know the vertex of the equation, or of the parabola. So I'm going to set up the template for vertex form. Y equals a times x minus 8 quantity squared plus k. And then I can go ahead and put in what the vertex is. So I actually know that this is y equals a times x minus 4 quantity squared plus 2, since hk is the vertex from lesson 2.2. And so all I need is the steepness, and I haven't used this piece of information yet. So I'm going to go ahead and put in the point 0, 6 for x and y and use that to solve algebraically for what the steepness is. If I do that, I get 6 equals a times quantity 0 minus 4 squared plus 2. And negative 4 quantity squared is 16, so this is actually 16a plus 2 would equal 6. Subtracting 2 on each side means that 16a would equal 4, and so a would equal 4/16, or 1/4. That means I can go back and put in that, the a value, and I can complete the equation. So y equals 1/4 times quantity x minus 4 quantity squared plus 2. This would be my equation in vertex form for that parabola. We're going to talk a little bit at the end of the lesson about how you can switch from one form to the other if that's not the form that you want it in. But in this case, if it just says write the equation, then we're going to pick whatever form is easiest and we're going to leave it in that form. Go ahead and try the second example. If you want to pause the video, go ahead and try it. Second example, and then we'll go over it together. If you have unpaused, let's go ahead and see what you've got. We're going to go ahead and start by putting in the vertex. So y would equal a times x plus 3 quantity squared plus 0. And you can see that since the y coordinate is 0, I don't actually need to write the plus 0. I kind of like to do that just to see the continuity in the form, but now after I've done that, I'll probably not go ahead and write plus 0 on all of them. I can go ahead and put in the point, negative 1, 4. So 4 is the y value of the point, and negative 1 was the x value of the point. Negative 1 plus 3 is 2, and then 2 squared is 4. So I get 4a equals 4, which means in this case, luckily for us, we get a equals 1. And I can go back up and put that in my equation. So I get y equals 1 times x plus 3 quantity squared plus 0, which of course really just means y equals x plus 3 quantity squared. The 1 and the 0 are unnecessary, so we don't really need to or want to keep them. And that would be our equation. That's in vertex form. You can also see that that's in transformation form because we can tell that the vertex has been shifted to the left 3 units. All right, so next task at hand is to write the equation of the parabola if I give you some roots and then a point on it. The roots help me to start making the equation, and then the point the extra point on it allows me to solve for the steepness value. So in the first example, let me fix this here, there you go. In the first example, the roots are 5, 0, and 9, 0. So I'm going to go ahead and start writing out the root form. I know that the template, just to remind ourselves from 2.2, the template for root form would be A times quantity x minus p times quantity x minus q. So if the root is 5, 0, and 9, 0, then I would go ahead and say that this means y equals a times x minus 5 times x minus 9. So now to figure out a, I'm going to use the point to figure out what that steepness is, which means I'm going to substitute in 5 for y and 4 for x. In this case, I have to substitute 4 for x in both times I see the x. So that would be 4 minus 5 and 4 minus 9. Simplifying that then gives me that 5 equals a times negative 1 times negative 5. So 5 equals 5a, and in this case a is just 1. So I can go back and put in, from this equation, I can put in a equals 1 and get that y would equal 1 times x minus 5 times x minus 9. And you don't need to write the 1 in there. If you'd like to put it in there to ensure yourself that you didn't actually forget to find a, then you are welcome to put that in there, but that would not be required. Here would be our equation. Again, if we need to change forms for this equation, I'll discuss that at the end, how we can flip from one form to the other. Go ahead and try the example problem on your own. Pause the video if you need to. All right, let's go ahead and look at this example problem. In this case, y would equal a times x plus 5, since the root was at negative 5, 0. And then if there is a root on the origin, then this would be x minus 0, which is also just x. But again, if you want to put it as x minus 0 just so that you're confident in the form, there's nothing wrong with that. And in fact, I think that's probably a good idea. And so now I'm going to go ahead and substitute in the point 112. So 12 is the y value, and then 1 would be the x value. So 1 plus 5. Sorry about that. Let's fix that. 1 plus 5, and then 1 minus 0. So I get 12 equals a times 6 times 1. And so if I divide both sides by 6, I get that in this case a, or the steepness factor, is 2. Then I can go back to the equation that I made from the top, and I can go ahead and put 2, and then x plus 5, and then I can put x minus 0. Now since x minus 0 is just x, I can just put x as well. And generally if I'm going to do that, I'd rather put it next to the 2 than to have it at the end, just because it looks a little bit nicer. So this is the same equation then as y equals 2x times x plus 5, and you'll just remember or remind yourself that that x means x minus 0. The third method would be that if I only had 3 points, how can I solve this equation? So let's practice one where I would only have 3 points. In this case, if I use 1, negative 1, 2, 2, and negative 4, 14. If I knew that one of those was the vertex, then that would be helpful. Or if I knew if 2 of those points had the same y value, then I could actually split the distance of the x values to find the axis of symmetry, because I know the symmetric nature of the parabola. But because none of the y values are the same, and I don't know if one of those points happens to be the vertex or not, I'm going to need to make a system of equations here. So I'm going to use standard form for this, y equals ax squared plus bx plus c. And I'm going to put in the x and y points, or coordinates, into those equations, and I'm going to do that for all 3 points. So if I use the fact that x is 1 and y is negative 1, then that produces the equation negative 1 equals a times 1 squared plus b times 1 plus c. And I'm going to simplify that, and I'm also going to put that in a form that we're more used to seeing from previous chapters, that this would be a plus b plus c equals -1. Then I can go ahead and do the second point. So the second point, 2 means that 2 equals a times 2 squared plus b times 2 plus c, when I substitute in for the x and y. And then putting that, simplifying and putting in a form that we're used to, this produces 4a plus 2b plus c equals 2. Last but not least, I can take -414, and I can go ahead and say that would mean 14 equals a times -4 squared plus b times -4 plus c, which then would produce 16a minus 4b plus c equals 14. So I have a system of 3 equations and 3 variables. 3 equation, 3 variable systems we did in chapter 1 of this textbook, so it's convenient that we already know how to solve those. If you are not required to show work, you can just type those into your calculator and use your calculator to help you solve the system. However, these systems are not going to be super difficult to solve because the c coefficient is always going to be 1, and we know that it's not going to be a no solution or an infinite solution problem. There's only one parabola that's going to go through these 3 points. I'm going to go ahead and take equation, if I label these as 1, 2, 3, I'm going to go ahead and take equation 1 and subtract it from equation 2. So that would produce 3a plus b. The c's would go away, and then 2 minus -1 is 3. So this is equation 2 minus equation 1 that produces that result. Then let's use equation 3, and so let's just do equation 3 minus equation 2. And that would lead us with 12a. -4 minus 2 would be -6b. The c's go away, and 14 minus 2 is 12. So now I can either eliminate b or a to continue solving. But I notice that in this second equation, these are all multiples of 6. So let's divide 6 out of everything to make this a little bit easier. So if I divide this by 6, this produces actually the same equation then as 2a minus b equals 2. That's helpful because I've got this 3a plus b equals 3 from up here. So 3a plus b equals 3. Turns out I can just add those and the b's are going to cancel out. I would get 5a equals 5, so a is 1. Once I know that a is 1, I'm going to back substitute into whatever equation I want that only has a and b. So I'm going to go up and just put it back in the 3a plus b equals 3. That means that 3 times 1 plus b equals 3. So 3 plus b equals 3, which means b is actually going to be 0 in this case. And then I can substitute a and b in one of the other equations to solve for c. So I'm going to come back up here to equation 1, and I'm going to substitute in the a, which is 1, plus b, which is 0, plus c, which we don't know, has to equal -1. And if I subtract from both sides, I get that c equals -2. Now that I know a, b, and c, I can write the equation in standard form. So I get y equals 1x squared plus 0x, so I won't bother to write that, minus 2. And if I want to check my work, or if I don't believe that I did this correctly, you can always substitute in any or all of the 3 original points and make sure that those 3 original points satisfy your table. Another thing that we can do with modeling is that we can use a difference table to kind of see what type of equation that we're looking at. So if we have a scatter plot and we want to see, is this a parabola or not, or is it a linear or not, one of the things we can do is make a difference table, which is checking out the change in y for any even change in x. So for the table on the left, I'm going to check that the x's are even distances apart, and they're all 1 unit apart, so I'm fine on that. And then let's look at the change in y. I'm going to label this as change 1. To get from 10 to 8, I would have to subtract 2. Similarly, I would be subtracting 2 from 8 to 6, subtracting 2 from 6 to 4, and subtracting 2 from 4 to 2. Because the first change is all even, then that means that the change in y is 2, or down 2, for every change in x that would be adding 1, since these were all consistently adding 1. That means that this is a linear function, and it actually means that the slope of the linear function is going to be that we're changing 2 units of y for every 1 unit of x, and so it would be a linear function with a slope of -2. If I wanted to find the exact equation, I could find the y-intercept, or then I could type this into my calculator and calculate the linear regression, which should have an r-squared value of 1, because this would be a perfect linear fit. However, in the case of this second example, if I make my difference table, I'm going to have something more interesting pop up here. To get from 26 to 17, I would be subtracting 9. To get from 17 to 10, I'm subtracting 7. From 10 to 5, I'm subtracting 5. And from 5 to 2, I would have to subtract 3. The changes in x don't have to be 1, as they are here, but they all have to be even, or this little trick doesn't work. Like, you couldn't have 1, 2, 4, 8. They would have to be even increments. In this case, they are all +1, so that's helpful to us. But the first change is not the same, and so since these are not the same, I can tell that this equation is not linear. However, I can test if it's a quadratic. If it's going to be a quadratic if the second differences are the same. So I'm just going to repeat the table and do some second differences here. To get from -9 to -7, I'm actually adding 2. And then to get from -7 to -5, adding 2. -5 to 3, I'm adding 2. And these are all the same number. And since they're the same, and it's the second differences that are the same, that means that this is a quadratic function. You can actually apply this to cubic functions and higher polynomials as well, that with a cubic function, the third differences are the same. With a quartic function, the fourth differences would be the same. Now that I know that it's a quadratic, you can use any 3 of these points and make a system if you want. Or you can put these points in your calculator and get the regression that way in your calculator. Or you can actually, once you find out that it's a quadratic, if you would like to continue the pattern, you could continue the pattern and work your way backwards to find the vertex and the steepness of this. So I'm going to show this to you. It's a little bit of a backwards way to do it, but it's how you could do it without your calculator. For the linear function, now that I've determined that it's linear, I just can add a few numbers up here to the top of the function, but I'll put them over here, that if I go back to 0, I would continue adding 2. Each time I'm going left 1 unit, I would continue adding 2, so that would be 12, 14, 16. And so in this case, I know that the slope was -2, and that the y-intercept was 16. For the quadratic, we got to do a little bit different, though. We need to figure out where the change is going to start, where this first change is going to go from negative to positive, because that's where we're going to find our vertex. So I'm just going to continue this on. I'm not introducing points and saying that points are on this quadratic that aren't. I'm only using the points in the table to determine that it's a quadratic. But once I've determined that it's a quadratic, then I'm allowed to go ahead and kind of think about what some other points in the table would be. So if I continued to add 2, because the second differences are equal, like so, then this would go from -5 to -3 to -1. To +1, to +3, to +5 for the first differences. And then if I think about what y values then would create those first differences, If I take 2 and I subtract 1, then that would take me to the y value of 1. And if I take 1 and add 1, it takes me to a y value of 2. And then 2 plus 3 is 5, and 5 plus 5 is 10. And so you can kind of see how these y values are lining up. The pattern in x would continue, that I would continue to add 1 each time. So this would be 6, 1, 7, 2, 8, 5, and 9, 10. And then looking at these points, you can kind of just see where the vertex is. Of course, this isn't going to work if the vertex is not on a nice, neat grid mark, right, if they don't have integer values. But for Algebra 2, this ends up working out most of the time. So I can see that 1 is the lowest value on the graph, and not only that, but it's centered in between. I've got 2 and 2, 5 and 5, 10 and 10, and we know from the symmetric nature of quadratics that those points that line up with each other are equidistant from the axis of symmetry. So that means, therefore, the vertex must be the point 6, 1. To find the steepness, I know that the steepness is what I get when I move over 1 unit from the vertex. So from the vertex, when I'm adding 1 to the x on either way, you can tell that I'm going up 1 unit, which means that the steepness, or the a value, is 1. So I can actually write the equation for this quadratic without my calculator by saying y equals, the steepness is 1, and then the vertex is 6, 1. So this would be x minus 6 quantity squared plus 1. I would use vertex form since that's what I know. With the calculator, we would put the points in L1 and L2, and we would choose, to calculate the regression, we would choose quadreg for quadratic regression here. Last but not least, I want just a little refresher on converting between forms. So if I have an equation, let's say, in vertex form, 2 times x minus 3 quantity squared plus 4 equals y. That's my equation. And I want to move that to standard form. I would move that to standard form, or convert that to standard form, by expanding everything out. That would mean at 2 times x minus 3 times x minus 3 plus 4. So I'm going to FOIL, or distribute the x minus 3 times x minus 3 first. That's going to produce x squared minus 3x minus another 3x. So I'm going to combine those like terms, so that's minus 6x. And then negative 3 times negative 3 would be positive 9. And now I can distribute the 2 to each of those, the 3 terms in the parentheses, which would be 2x squared minus 12x plus 18. And then I can combine the like terms, the 18 plus 4. So I get, if I carry on this equal sign and make a run-on sentence here, I get that y would equal 2x squared minus 12x plus 22. The graph of these equations, these are the same equation, just in different forms, but they would produce the same graph on your calculator. So now I know that the vertex is 3, 4 from vertex form. I know that the steepness is 2 from either form. And I know that the y-intercept is 22, which now I can see from standard form. That's to move from vertex form to standard form. To move from root form to standard form, we can do an example of that as well. So if I said y equals negative 3 times x plus 1 times x minus 7. My first trick would just be to go ahead and distribute the x plus 1 and the x minus 7, or FOIL if you want to call it that. So I'd have negative 3 times, and then x times x is x squared. The inner term would be 1x, and the outer term is negative 7x. So if I combine those, that would make negative 6x. And then the last would be the 1 times negative 7, which is negative 7. Then I can distribute the negative 3. So each term gets multiplied by negative 3, producing negative 3x squared plus 18x plus 21. I'll shift down my equal sign there. So I end up with standard form of y equals negative 3x squared plus 18x plus 21, means that the y-intercept would be at 0, 21. I can read from here. The roots would be negative 1, 0, and 7, 0. The steepness is negative 3. I can read that from either form. But these produce the same graph. It's just looking at them in different forms. We would not necessarily need to ever convert from root form to vertex form. But sometimes it is helpful to convert from standard form to vertex form. So there are two good ways of doing that, from standard to vertex. The first, let's say y equals x squared plus 6x plus 3. The first way is probably the way that you'll want to stick to for the time being. The first way works fairly nicely, and that's to solve for the vertex from standard form, just like we did when we were graphing, and then go backwards and just put those numbers back in vertex form. So it's kind of working a little backwards workaround here. So I would say I know that x equals negative b over 2a would be the x coordinate of the vertex. In this case, that would be negative 6 over 2 times 1, or negative 3. So I know that the vertex is negative 3 something. If I substitute in negative 3, I would get y is negative 3 squared plus 6 times negative 3 plus 3. So that's 9 minus 18 plus 3, which would equal negative 6. So I can find that the vertex is negative 3, negative 6. And I also know that the steepness in this case is 1, just because I'm reading that from the original problem. The steepness never changes. So I can write this in vertex form by just copying down the steepness, making sure that stays the same, and then switching it over to vertex form, saying, well, negative 3 is the x coordinate of the vertex, producing x plus 3 quantity squared. And then negative 6 is the y coordinate, producing the minus 6 at the end. That's one way to convert from standard to vertex. The other way to convert from standard to vertex is called completing the square. And completing the square is a different topic that sometimes people think is make it harder than it needs to be, but it's actually not that bad. So with the same example, y equals x squared plus 6x plus 3. Completing the square is only going to be a really good option for you in this case when a is 1 and b is even. It's some sort of even number. You can do it when it's not, but that's what we're going to be sticking to for now, when a is 1 and b is even. So what we're going to do is we're going to take half of b. You may have, when you learned how to multiply polynomial expressions, you may have done some multiplication by making a little something that looks like a Punnett square. And I would say that, for instance, x times x is x squared. Well, what I want to do in factoring, or in completing the square, is kind of to pull out the outside from the inside. So I want to take the 6x that I have here, and I want to split it in half, which would put 3x and 3x on my diagonals. And if that's the case, then this would mean that the outside number would have to be 3. So the x times 3 is 3x, and x times 3 is 3x. Then if I am completing the Punnett square, then I would have to do 3 times 3, which is 9, and so guess what the number 9 does? The number 9 completes the square. So that means if I had x squared plus 6x, if I had a plus 9 there, then this would be a perfect x plus 3 times x plus 3, or x plus 3 quantity squared. It would make a perfect square because I would have the same factor on each side there, the factor of x plus 3 and the factor of x plus 3. But the trouble is, the little trick is that we can't just add 9 for the heck of it, because that changes the expression. So we would just subtract 9 right after it, like so, and then it evens out, so that's actually legal. And then the first three terms here turn into the x plus 3 quantity squared, and then the last two terms, we would just simplify the leftovers. Turns into x plus 3 quantity squared minus 6 equals y. If you look back on the previous page where we were finding negative b over 2a, you can see that we got the same example, or the same answer. My preference is completing the square, especially when a is 1 and b is even, but I'll leave that up to you which one you want to do. And that will convert from standard form to vertex form. So there it is, there's 2.4 in a large nutshell.